Okay, we can start.
Yep.
Thank you.
Cheers.
Hi everyone, I'm Joseph Wood. I've come from Imperial College in London and I'm looking at the effects of cracking in paintings due to relative humidity cycles. So here's the contents of my presentation. Initially I'll give a brief overview of the crack types in paintings and painting construction. Then I'll discuss my models, how we're modelling the painting and looking at certain types of crack growth within the paintings. Then afterwards I'll give some of my results and the relative humidity cycles that we are exposing the paintings to, a comparison of crack initiation times between crack types, and then a parametric study on a through thickness crack, and finally I'll conclude. So, paintings are complex, multi-layered structures, and due to the hygroscopic nature of the layers, strains are set up in the paintings, and due to the different dimensional response due to humidity cycles, strain differentials are induced between the layers, and this causes shear stresses along the interfaces and then leads to a delamination in the painting. So here I have 3 examples of delamination, the first of which is Charles III. Here if we look, we see that the paint has peeled off and a blue layer has been exposed. Then if we consider Sir Christopher Hatton at the bottom, we see that the paint layer has come completely off and the wooden substrate can be seen. And then finally, if we look at Queen Elizabeth I in the top right-hand corner, we see this dark paint layer exposed due to the gilding being removed. So the second type of crack that we see in the paintings is a through-thickness channeling crack, and this occurs due to tensile stresses in the paint layers. So here are 3 examples again. Here we've got Sir Francis Drake, we've got cracks in the red-brown spandrel. On Thomas Cromwell, we've actually got cracks in the portrait oval, and these cracks follow the grain of the wood that the painting is on. And then in the third case, we have Henry VIII, where there's cracks in the gold gilding on top of the painting. So, painting construction. Initially, you have the substrate or support, which is either usually canvas or wood. The movement of the wood due to relative humidity is dependent on how the panel has been cut. So this is usually either radially or tangential. However, when you consider canvas, we're considering a homogeneous material, and on top of this, a sizing layer is then put onto the wood to prepare the wood or canvas to prepare the support for the paint. This is usually an animal glue. Afterwards, a ground layer is applied, which is either calcium carbonate or calcium sulfate within a binding material. And then finally, you have the colour pigments in the design layer in the binding material as well. Choices of binding material include animal glue, egg, drying oils, acrylics and alkyds, and this is very much dependent on the finish that the artist is going for, and also on the time that it's painted. So our model construction, we're just considering 2 layers. First, we have the substrate or support, and we're looking at a canvas. The canvas has been primed with an acrylic-based calcium sulfate ground layer, and we're just considering this as 1 layer. From literature, we've identified that this can be considered as linear elastic with a Young's modulus of 3.6 gigapascals, Poisson's ratio of 0.3, and it shows little effects to changes in relative humidity. On top of this, we have an alkyd design layer. This is being modelled using a visco-hyperelastic material model. This is due to the fact that the paint experiences time-dependent behaviour and also large deformations. Furthermore, the paint layer shows a dimensional response to changes in relative humidity, so we also have a hygroscopic expansion coefficient. So, for a viscoelastic material, it is possible to separate the strain and time-dependent functions. The time-dependent function can be represented by a Prony series, which can be seen here, where T is the time, tau is the relaxation time, and G are dimensionless parameters. The stress response for an arbitrary strain history can be expressed using the convolution integral here. This is the long-term stress response. And then the function sigma naught can be obtained from the van der Waals hyperelastic potential, as seen here, where psi is the instantaneous shear modulus, lambda is the stretch ratio, lambda m the lock-in stretch, and alpha is a global interaction parameter. So we calibrate this material model using tensile test data of a free alkyd film. So this is previous work by Tanta Derivatives et al. 2013. These relaxation times represent the total time in testing, and here we have the van der Waals strain energy potential parameters. So my models use the cohesive zone model, in which we place elements in a location where a crack is expected to grow. So if we look in the top right, obviously for the interfacial crack, we place elements along the interface, and for a through thickness crack, we place elements through the thickness of the film. So the response to the elements is controlled by a traction separation law. We consider a bilinear traction separation law, as seen in the bottom right-hand corner, where the fracture energy is the area under the graph, the initial element stiffness is K, monotonic damage begins to accumulate at a separation delta naught, failure at delta sigma. However, as we're considering fatigue cycles, if the element is cycled at separations lower than delta sigma, then this will give an infinite fatigue life, which isn't what we see in the paintings. Therefore, we have to modify this. We do this using the irreversible cohesive zone model. So it's a modified cohesive zone model to include the fatigue damage variable DC. This means that traction separation parameters now degrade under cyclic loading, and how they degrade is controlled by this parameter, which is delta DC, which we've taken from literature. Therefore, the stress response in the element is now degraded from the monotonic case and the fatigue case. Therefore, if there's no monotonic damage occurring, the stress is still degraded now due to DC. And you can see this in the case that the element stiffness has been changed. Okay, so now we're considering the interfacial crack. So we have elements along the interface between paint and canvas. Previously, traction separation law parameters have been obtained by comparing peel test experimental results to that from the finite element method, and they've come up with these parameters. Here we have a picture of the finite element model used. We've got a paint, canvas, and then along the interface we have zero thickness cohesive elements. Okay, for the through thickness crack, we have cohesive elements through the thickness, and we're modeling the interface with perfect adhesion. So initially, as we have no fracture properties so we don't have the through thickness fracture properties of the alkyd paint, we're just going to use the same traction separation law as the interface. Afterwards, we're going to look and do a parametric study on the parameters. Okay, so here we have the finite element model used. This is the crack, and I do have a video just to show cyclic loading of the model, if it runs. Yeah, you see the crack opens and then compresses and then opens. So it's just cyclic loading. Okay, so now we have our two models. We have to identify what relative humidity cycles that we want to input as a boundary condition. So we know that for a calm day, relative humidity is inversely proportional to temperature. Therefore, in the morning at 6 o'clock, when the temperature is lowest, relative humidity is at a maximum. And then in the afternoon at 3, temperature is a maximum, relative humidity is a minimum. So therefore we have this cycle that we can input into the finite element method. So for a calm day, we put in a minimum relative humidity in at 35% RH and a maximum of 90% RH. Then to consider some other relative humidity cycles, we've looked at museum policies that they try and keep paintings under. So if we consider the V&A Museum in London, the paintings are not allowed to get below 40% RH and not above 65% RH. So we input these values as minimum and max values in the day cycle. We're also looking at a strictly controlled museum, which is a minimum of 45% RH and then a maximum of 55%. So initially we're looking at the same traction separation law for both interface and through thickness cohesive elements. So we know that interfacial cracks are dominated by mode 2 and through thickness cracks dominated by mode 1. So here if we look at, here we have the parameters used in the traction separation law, and we have the 3 relative humidity cycles. Here is the time to crack initiation. Initially, for the most extreme case of 35% minimum, maximum 90%, we see that interfacial fracture happens before through thickness cracks. However, when we look at the smaller range of relative humidity, we see that there's actually a change, and the through thickness cracks seem to occur before the interfacial cracks. So now we're going to do a parametric study on the through thickness cohesive parameters. So the cycle that we've decided to use is the extreme case with 35% as the minimum and 90% as the maximum. Firstly, we're going to vary sigma m, delta sigma and k naught. We're going to keep delta naught and the fracture energy G as a constant. Here we have the interfacial properties I previously showed you. And on the right hand side, we have how the maximum stress in the cohesive elements degrades over time. So we're looking at failure of the element when the maximum stress degrades to 0. So if we look at the case of 0.5, sigma m equals... Yeah, so if we look at the case for sigma n equals 0.5, which is a 50% reduction, we see that there's a 35% increase in the time to first crack. So this is the base case, and this is 50% decrease in sigma m. If we increase sigma m by 50%, we see an increase in decrease in the time to first crack of minus a decrease of 14%, and as we increase sigma m to 2, this decreases the time by 26% compared to the base case, and then the last one decreases it by 40%. So now we're going to look at the effect of the value of delta naught on the through thickness cracks. Again, we're considering the same cycle. We vary in delta naught, and then obviously if we're varying delta naught but keeping sigma m constant, we're also varying k. So we've got the fracture energy is a constant and delta sigma is constant. Here's the interface properties again. We see that if we half the value of delta naught compared to the interfacial property case, we see an increase in the time to crack initiation by 28% and a decrease. And if we increase delta naught by 50%, we see a decrease of 11% in the time to crack initiation. Finally, if we look at the effect of delta sigma on the through thickness property, on the time to crack initiation, sorry, we're looking at the same cycle. We're varying the fracture energy G and delta sigma and keeping sigma m, k naught, and delta naught constant. We see that if we decrease delta sigma by 50%, we see a minus a decrease of 66% in the time to crack initiation. And if we increase it by 50%, you actually see a 66% increase in the time to crack initiation. And if you double it, you actually see a 132% increase. So in conclusion, I've shown that the main crack types in the paintings are through thickness channeling crack and an interfacial crack. I've presented 2 models, both of which have a linear elastic canvas and a visco-hyperelastic alkyd paint layer. I've considered time to first crack and performed a parametric study on the through thickness cracks. And now we've just started to expand the models to consider multi-layers on top of the substrate, and also a wooden substrate, which increases the complexity of the model considerably, because it depends on how the wood's been cut, as I previously said. And then we're going to perform fracture tests in order to obtain the fracture energy for the interface and the through thickness. Thank you.
Thank you for your nice presentation. We are on time.